Thank you very much. My name is Liam Zarri. I'm a master's student at the Bycatch lab at UC Santa Cruz, and I'm interested in the impact of temperature management on green sturgeon in the Sacramento River. I'd like to start off by thanking collaborators at the National Marine Fisheries Service, Eric Danner, who has funded this work so far, Carlos Garza and Bill Poitras for samples, and the Bycatch lab at UC Santa Cruz for providing writing, statistical, and moral support. The Endangered Species Act typically protects umbrella species. By creating habitat for one species, an ecosystem can be protected. For example, spotted owl in north coast forests and tidewater goby in estuaries along the California coast. But what happens if an endangered species doesn't exist in its ancestral habitat? Winter-run chinook historically spawned in cold upper Sacramento River tributaries, requiring below 13 1/3 degrees centigrade temperatures for egg and fry development. However, after Shasta Dam was constructed, they were forced to spawn in the warm main stem habitat below the dam. After they were listed as endangered species in 1994, after their population declined, a temperature control device was installed on Shasta Dam to decrease the water temperature outflow from the dam. The summer temperature is managed at the upper limit of their thermal extreme, 13 1/3 degrees Celsius, from Keswick Dam, which is in Redding, or right above Redding, all the way down to Red Bluff, and river discharge is increased to meet this goal. Here you can see two representative years of pre versus post temperature compliance. In the red, you have pre-temperature compliance. In blue, you have post-temperature compliance. And you can see that the temperature levels off at this 13 1/3 degrees Celsius. Also occurring in this area are green sturgeon, also an endangered species. They evolved to spawn in these warm main stem rivers on a spawning migration from the Pacific Ocean. The larvae develop and rear inside of this temperature managed zone and just below it before moving down the river to continue their life cycle. Larval development of green sturgeon has been experimentally shown to be optimal between 15 and 19 degrees Celsius. It's been suggested in other studies that cooler temperatures as a result of this temperature management may pressure larval sturgeon out from these upriver incubation areas and limit the upper extent of their spawning habitat. Here you can see the spatial overlap between the temperature-controlled zone and sturgeon spawning, extending from about Jelly's Ferry to Red Bluff. Here's the temporal overlap. The temperature management time period goes from June to October, which overlaps considerably with larval sturgeon in that system from May to August. Unfortunately, I can't directly test the impact of temperature management on this species, which is why perhaps one reason why this question hasn't been addressed yet. The reason is that the temperature before temperature compliance the temperatures are not above where temperature compliance happens. You can see that temperature simply levels off as opposed to being warmer and then decreasing with temperature compliance. So instead, I attempt to address this question by understanding how a decrease in temperature and an increase in discharge impact green sturgeon larvae in this wild system. My first attempt at this is to use the California drought as a proxy to compare a cold year when management was effective versus a warm year when management was not effective. The California drought significantly reduced the effectiveness of temperature management by decreasing the amount of cold water that could be released. Temperature management, as a result, was not nearly as effective from 2014 to 2016, as you can see in this graph. Temperature increased significantly from 2014 to 2016 when compared to pre-drought years, and discharge decreased significantly. My methods for this study were using samples that came from bycatch mortality in screw traps at the Red Bluff Diversion Dam. I measured condition factor, which is an indicator of health in fish. It's a measure of fatness, essentially. A larger condition factor is more mass for a given length. Condition factor, total length, and diet contents were all used for this study. The environmental variables came from temperature and discharge measurements from the National Marine Fisheries Service Temperature Model, or RAFT, at Jellies Ferry. To only address the fish, to only estimate the fish that were within a particular time period, I only used fish from 20 to 40 millimeters long, which is approximately the size range of 2.5-week-old fish, which is how old the fish that are being caught at Red Bluff Diversion Dam are estimated to be. I used the environmental variables averaged across the 2.5 weeks prior to this as well. So, when using the drought to estimate the impact of temperature management on green sturgeon, I first compare temperature management against condition factor here and found that there's a significant impact to the drought. Condition factor was increased during the drought by approximately 0.07. Further, green sturgeon did better in the drought when estimated by total length. They were longer during the drought as measured at this particular point. So we can say that total length and condition factor are higher in drought years. However, drought, of course, is simply a binary classifier. I need to correct for the year effect and use continuous explanatory variables to really look into this situation. Discharge and temperature are, of course, moderately collinear. I'm interested in the impact of both, however, so I ran models separately with temperature and discharge. First, condition factor varies by total length, so I corrected for the length effect by taking the residuals of linear regression with total length, thus achieving a corrected condition factor. A positive value is fatter than expected for a given length. A negative value is skinnier than expected for a given length. I then regress this against temperature, this corrected condition factor against temperature, finding that condition factor is higher in warmer temperatures. And positive condition factor is found above 15 1/3 degrees Celsius. I ran the same with discharge, finding that as discharge increased, corrected condition factor decreases, and it's positive at lower discharge, below 8,300 cubic feet per second. But which is more important? Is the temperature or the discharge more important in impacting this corrected condition factor? I ran a mixed linear model using corrected condition factor and two separate models, one with temperature, one in discharge. And by using a corrected AIC, found that temperature was a better fit to the data than discharge. So this seems to suggest that corrected condition factor, positive above primarily 15 1/3 degrees Celsius and below 8,300 cubic feet per second, is beneficial for larval sturgeon. But what is the mechanism here? Of course, temperature and discharge is impacting an entire ecosystem, not just the sturgeon. It could be impacting their metabolism, or it could be impacting the ecosystem that they rely upon for food. Of course, it's probably somewhere in between. I attempt to address this question by also looking at diet contents. At first, I did a binomial assessment. Simply, is there something in the diets, or are the diets empty? I found that the drought, back to the drought, impacts whether diets are full or empty. There were significantly more diet fullness during the drought, 8.7%. More diets were full during the drought. After correcting for total length, temperature once again seems to be driving this relationship, as determined by the corrected AIC. The next step for this is to run an actual zero inflated model to understand how both the empty diets and the full diets, and then the continuous amount of diet fullness is driven by temperature versus discharge. But that's the next step. Finally, I asked how were diet items impacted by the environment. The main diet items of larval green sturgeon in this system are primarily cyclopoid copepods, betids, chironomids, and then finally some mulids. Copepods and chironomids were both significantly impacted by temperature in the diets and impacted by discharge. So the takeaway from this seems to suggest that the environment that's created by temperature management for winter-run chinook is negatively impacting the green sturgeon. This is an interesting system not only to understand this management relevance, but it's also a fascinating ecological system if future studies are to go on in this system. What happens when you take an entire ecosystem and decrease the temperature? How does that impact the trophic linkages between primary producers, herbivores, and predators? And I hope this work continues to go on. Thank you.